two dimensions. These are pretty similar to what 2D arrays and 3D arrays are declared in Python or in C++. And honestly, the underlying data type is probably just uh, multiple dimension arrays, but they're rapid or inside the torch tensor. And it has a lot of very interesting operations that support the torch class. So yeah, so there are multiple ways you can create tensors. You can just use arrays or lists like this, or you can create them from non-PY arrays. Yeah, pretty interesting. So here's an interesting note is when you declare or when you declare Pytorch arrays from NumPy arrays, they actually are the same copy, the same item. So they share the same memory location. This is more like a wraparound of the same memory location. Yeah. So if you want to create a deep copy, you should use clone, or just call what we will call a constructor function, right? Rather than just like from NumPy, you use this one. So, um, interesting. So this is also an initialization functions where you just call the zeros and provide it with shapes, right? You can give it two shapes. I wonder though, if I want to create like okay, so it will actually do that. Okay, so you can basically just pass in the dimensions uh, for zeros, and it will just give you zero initialized arrays, or in this case, tensors. Okay, ones and all that. So, and also you can just give it arbitrary fill number. Wow, these are pretty interesting. Um, Yeah, and also, identity matrix. So just only ones across the diagonal and zeros uh, other places. Okay. Yeah, and here this section talks about how you can generate random tensors, um, which are crucial for weight generation, weight initializations. Yeah, and you can actually define the distribution, right? You can use uniform distribution, by binomial or normal distribution, or just random things. Kind of interesting. Okay, so far we talk about like the basics of tensors, right? These are not really interesting. Just tell you how you can examine the shapes and like dimensions and total numbers and all that, and the data types. Um, yeah, and here we talk about data types, right? Now very interesting. Uh, Oh, here we found something interesting. Slicing and indexing. In a previous notebook, we talked about this in NumPy notebook. We've seen this, but with Tensor, like I said, it has better support for built-in, right? You can access the Tensor elements. For one-dimensional, you can just use random access like this. You also get a slice of it. Now, the original syntax was like this, but it was a syntax error. I don't know. The step number has to be greater than zero, so it was throwing a syntax error. So to really flip a tensor, you will have to call torch flip the original tensor. Yeah. Uh, but so I was wondering, okay, when I call this operation on the original tensor, does it actually flip the elements in place on the original data set, on the original one, or it's doing on a copy? So I asked Gemini, and they told me that it's actually returns a new tensor. So the original one was left intact, and it just throws me a section that to examine that torch flip actually does not modify the original tensor, right? So after the flip, the origin tensor still looks the same. And also, they're not same object. They do not share the same memory locations. So yeah, this is a little diverge from the syntax of flipping the tensor. Okay, so you can slice it however you like. You can randomly select the columns. Okay, so this is actually how you select the column. That's very interesting. Um, yeah, very interesting, very interesting. Because as you can see here, fancy indexing, it was a lot more tedious to try to do the same thing. Hmm, actually do wonder. So if I do this, does it let me do that? No, it does not. Okay. So yeah, with fancy indexing, it's pretty easy to select rows, but if you want to select columns, like a single column, you'll have to do it this way, which is pretty annoying. It's exactly the same as selecting a specific element. So yeah, with fancy indexing, it's not fun. It is not fun. Yeah, much easier if you can do it this way. Hmm, interesting. I wonder why they wouldn't let you. Hmm. Anywho, yeah, and also can do Boolean masking. Oh, this is fun. Okay, then we have the mathematical arithmetic operations on tensors. Now this is where using Pytorch tensor is probably better than using NumPy because a lot of this operators has been overloaded to actually do the matrix uh, arithmetics arithmetics. So yeah, so by default, the multiplication works in this way, I guess. Although this is a little confusing, because if you do matrix multiplication, really the dimension has to match on the inner side, but these are all 3 by 1 matrices, so this I don't know. I don't know about this, man. That shouldn't work. Uh, but yeah, you can also do this. So these are just like, yeah, like a map function to map all the uh, operate math operations on all the elements. Right? Here is the aggregation functions. Aggregation functions essentially looks at the entire matrix and just output a single number or like really a reduced dimensioned uh, tensor, right? So yeah, mm, tells you how to do the dimension reduction. Okay. Uh, so here we move on to broadcasting. Like we said in previous notebook, it's the same thing when you try to add a bias, it's basically stretch the bias, the smaller dimension one, and the bigger one. Yeah, that's good. But it has to at least match on one dimension, I guess. So if in this example, we have 1, 2, 3 plus all this. So it's really 10 plus 1 and 10 plus 4, 20 plus 2 and 20 plus 5 and all that. So yeah. So in the above cell, we talk about how torch flip does not modify the original one, the original tensor. So that operation was not in place. So here we talk about some of the in place operators, and the trick is to just like add an underscore before that. Yeah. So all of this is just in place modification. And also you can reshape the tensors and flatten the tensors and squeeze and unsqueeze them. Okay, transpose. Transpose is just swapping the rows and columns, basically a flip on the diagonal, right? Uh, yeah. And here we have concatenation and stacking. Very interesting operators. So now, here, okay, this was I was worried about. So, in Bob, we have the bitwise multiplication. That is not matrix multiplication, right? The matrix multiplication, like we said before, it has to be, they have to match on the inner side, so the inner dimensions, right? And the operator here is this, not the multiple one. So it's matrix multiplication instead of just multiply. Uh, yeah. So yeah, dot product, same thing. And you have normalizations, you know. Here, you have L1 and L2. That's interesting. P equals 1. P equals 1 is L1 or, huh, that's interesting. Yep. So after normalization, you basically have the tensor of the vector like a unit vector, basically. Yeah, of the same direction. So also other operations like determinants, inverse, and all that. Yeah, and trace. And you also have eigenvalues and eigenvectors. Ooh, that's great.